This unit, we're going to start a new unit, I guess, but the new unit is called chemical nomenclature. Nomenclature has to do with bonding of different atoms together to form a chemical compound. So we kind of started off our year as elements, which are kind of like letters, and then we're putting those letters together right now, and we're going to start to form compounds, or what I call words. Eventually, we're going to use these and we're going to make chemical sentences, which are our chemical reactions. So as we're looking at your nomenclature unit, there's a few, little bits of terminology that you need to get out of the way first, and then once we get that terminology out of the way, then we're going to actually get into the bulk of the nomenclature unit, and we're going to look at ionic bonds, and then we're going to look at covalent bonds. So as we look at this unit, you have your just chemical bond definition first. With your chemical bond, it's just two atoms that are chemically combined together. You cannot break a chemical bond without going through a chemical reaction. They are very, 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 very strong. Again, you can't just break them by, adding water or anything like that, but it's an actual force that holds things together. The force is kind of like a magnet. They're not really visible, you can't really see them, but they do exist, and it is because of a transfer of electrons on the valence shell. So as we're looking at that valence shell, the magic number for everything except for hydrogen and helium are 8 valence electrons. So a full valence shell is 8 valence electrons for everything, again, except for hydrogen and helium. They're only good with 2. Everything else wants that full valence shell of 8 valence electrons. So it's called an octet. Oct, O-C-T, is 8. So with your octet with a full valence shell of 8 valence electrons, again, except for hydrogen and helium, you are striving to form an octet in multiple ways throughout this unit. Whether we're going to share electrons or we're going to transfer electrons from one to another, either way, everything is going to get that full octet no matter what. So with the first type of bond that we're going to look at, your ionic bonds, these come from positive and negative forces. Your positive forces were called cations, your negative forces are called anions. Opposites attract, they're going to stick together again like a magnet does. So those ions that occur when an atom loses electrons, so they get transferred to something else, these are called cations. Cations have positive charges because they lose negatively charged electrons. You have more protons than electrons. So when you are losing electrons, I didn't really tell you this in last unit, it kind of came up when we were talking in class, but for the at-home people you didn't get to hear that. The electrons themselves on that valence shell transfer to something else, and I told you last unit, just don't worry about it, where they're going, we'll get to that later. Well, it's later now. So those electrons on the valence shell are actually going to leave one component of the atom and it's going to go to something else, and when it transfers those electrons, that's what creates that negative and positive force. They stick together. So when you're losing electrons, it's just striving to get that full valence shell for stability. So what it's trying to look like is the noble gas family. With the noble gases, they have those full valence shells. Remember, they're really small because they don't want to lose any of their electrons that are on that shell. They don't react with anything. The reason why they don't react is because they have that full valence shell. So with your periodic table, we're going to kind of jump to my, I've got a periodic table here that we'll look at that we colored last unit. But when we talked about the oxidation numbers last unit and we talked about the periodic table with metals, nonmetals, and metalloids, we said that if you have a metal, if you have anything on the right side of the periodic table, it's a nonmetal. Anything on the left side of the periodic table is a nonmetal, except hydrogen is kind of in a weird spot. That actually goes with the nonmetals. And then we had the metalloids in the middle. We're going to get rid of the metalloids now. We're going to act like they don't really exist anymore. We're going to lump them in with one or the other. So I'll get to that when we get to the periodic table. But when you have your metals on the periodic table, all metals, no matter what, they all form cations. So all of your metals will always lose electrons. Typically they lose one or two, sometimes they can lose more, but no matter what, they always lose electrons. So when we're looking at the periodic table, again, I'm going to jump over to my document camera here in a second, but when you have your metals, all of these on the periodic table, they all form cations. So if I bring up my camera here, if I can move this over a little bit so you can see. So we've got the metals, nonmetals, and metalloids, and this is what you guys colored in the last section. You had some notes and you described the metal characteristics, you described the non-metal characteristics, and then you had the metalloids in the middle. We're going to kind of scratch this middle section right here with your metalloids. What's going to happen now is we're going to break up the periodic table still with a stair-step line, but when we break up the periodic table with that stair-step line, everything on this side of the stair-step are all nonmetals now. So everything that I have colored in yellow with hydrogen down here, they're all nonmetals. Your metals are everything on this side of the stair-step line. So everything that I have colored in pink on this periodic table all form cations. They all lose electrons. So this might be a little bit of a spoiler alert, but your nonmetals, they all form a negative charge. So when we had your oxidation numbers, we said that everything in group 1 all have a +1 charge. Group 2 all have +2. Group 13 all have +3. 14 is plus or minus 4. 15 is -3. 16 is -2. And 17 is -1. Those are your oxidation numbers. So if I fill these in here, everything in group 1 I'll have a +1 oxidation number. I'll come back and talk about hydrogen. Hydrogen's kind of a weird little guy up here, but it does form a +1 charge. Everything in group number 2 are all +2. We're going to skip your transition metals for right now. They're going to cause us a little bit of a headache, so don't worry about them for right now. Group number 13, the metals are all +3. Boron is another kind of weird element. You don't need to worry about boron for this class pretty much ever. Boron, because it has so many exceptions to it, we're just going to kind of ignore its presence for right now. Carbon, this group right here, if it is a metal, metals, they have +4 charges. So that means that germanium is +4, tin is +4, lead is +4. So if it's a positive charge, it's a metal. So jumping back to our notes, just did that. With your representative elements, the elements that live in the S block and the P block, those get named very plainly. They don't have anything special that go with them at all whatsoever. They're going to be the easiest type of naming that we do at all whatsoever. So when we go to name these, this little +3 that I have here, you just kind of ignore it. This is just called an aluminum ion. It has a +3 charge. It has a charge. So this is called an aluminum ion. If it just was Al, it's just called aluminum. But because there's a +3, it's called an aluminum ion. So this guy down here, Na is sodium. This is called a sodium ion. Real difficult, right? It's really easy. All right, now your transition metals. These have different numbers of electrons that they can lose. Some of them always have the same charge. Some of them can vary depending on how they are bonding or what they're bonding with. So if you have like nickel, you can have nickel with a +1 charge. You can also have nickel with a +2 charge. You could have nickel with a +3 charge. But if you have zinc, zinc is always +2. So they have different numbers of electrons that they can lose. Typically it's 2, but 1, 2, and 3 is kind of the most popular with those. So because of that, when we name them, we have to name them using what's called a Roman numeral. Your Roman numerals, you're going to have to know. They are numbers 1 through, usually about 8 is about all that you need to know in order to get through your nomenclature for this unit. But your Roman numerals, you're going to tell the charge of the element that you're dealing with. So if you had something like, I don't know, titanium with a +1 charge, you would write out titanium. And then in parentheses after that, you would put down a 1 or an I in Roman numerals. And that's just saying, hey, titanium lost 1 electron in this case when it bonded. So we will need to know our Roman numerals. I'm going to jump over to my paper here. And when we look at this, I'm going to write down my Roman numerals so you can see them. Roman numeral 1 is just an I. Roman numeral 2 is II. Roman numeral 3 is 3 I's. And then you have 4, I'm going to write down 5 and 6, because these are the ones that people get confused about the most. 5 is V. 4 is 1 before 5, so it's IV. Random bit of knowledge that I know. Blue Ivy, Beyonce and Jay-Z, I think his name was, had a baby and they could name the kid Blue Ivy. It's because the number 4 was really important to them. They were like, I don't know, they both have like April birthdays or something. I don't know what the deal is. There was something very important with the number 4. So they named the kid Blue Ivy because of IV, number 4. You can look up more information about that. I just remember hearing it and going, oh, that kind of makes sense for what we talk about in class. So back to the topic. Your 4 is IV. 5 is V. 6 is after 5, so it's VI. Again, people always confuse those, but we read from left to right. So this is 1 before 5, this is 1 after 5. Just to round out to 10, just in case you're curious, 7 is VII. 8, 3 of your I's after V. Now 9 and 10, 10 is X. So 9, 1 before 10 is IX. Again, you won't really ever use 8, 9, 10. Pretty much if you can get through 7, you're good. So how we name these, by using those Roman numerals, if I have something like Cu plus 2, copper is a transition metal. With copper being a transition metal, I'm going to use Roman numerals. Write this down just so we have it. Anything through here, you're going to use Roman numerals for. So because I have copper with a +2 charge, this is called copper 2. Here, copper, again, is still a transition metal. This one's called copper 1 because it's copper with a +1 charge. These match. +2, 2. +1, 1. So down here we have iron 3 ion. So if we have an iron 3 ion, iron is Fe. That 3 tells me that I have a +3 charge. Same thing here, iron 1 ion. If I have an iron 1 ion, again, iron is Fe. This 1 means that I have a +1 charge. Vanadium V ion, so that reads vanadium 5 ion. Vanadium is V. It has a +5 charge. So this tells me the charge, or the oxidation number. The oxidation number is how many valence electrons it loses. So just a couple more and then we'll be done. With your transition metals, there are 2 of them that you need to know. Zinc always has a +2 charge. This is going to come into play next unit when we start to predict products of your chemical compounds. It's going to say, like in a lab, you know, zinc, I don't know, and oxygen are combining together. People are going to go, I don't know the charge of zinc. Actually, yes, you do. Zinc is always +2. Silver always has a +1 charge. There's no other format or combination with those at all whatsoever. So zinc is always +2, silver is always +1. When we look at the periodic table, their placement kind of helps you to remind you of that. So aluminum is here, zinc is here, silver's here. Aluminum is a representative element. It always has a +3 charge. So it doesn't get Roman numerals because it's just aluminum. Aluminum is always +3. Zinc is +2. So +3, +2, hey, silver's plus 1. So they're kind of all in a row, 3, 2, 1. I will warn you, if you Google answers with some of these nomenclature things, a lot of times it's going to come up with organic compounds. Other times, some of them, like if you have a college professor, sometimes they don't make you write zinc 2 in parentheses after it. I'm going to say no, it's wrong. You have to use Roman numerals anytime you have any of these transition metals. So it has to be present even though it's always there. I just keep all of my rules consistent all the time just so you don't have to remember, oh, there's this exception, oh, there's this exception. It's just a lot easier. So don't Google, just do your work. All right, one more slide here. Nope, I did that one. Oh, this was the last one. I've kind of said this over and over, but the charge, the plus 2, plus 3, plus 1, even if it's negative, -1, -2, -3, those charges are all called oxidation numbers. In the next video, we're going to look at anions, and then after we look at anions, we're going to start to put these together into compounds. So I'll stop it here, and we'll do a separate video for your chemical compounds.